Okay, welcome to question 1 from example sheet 2, refrigeration. Notice we're given refrigerant 134A as a working fluid, and most importantly we're looking at the ideal vapor compression cycle, refrigeration cycle between the pressure values given. The mass flow rate is also given as well, and we're asked to show the cycle on a TS diagram. I would always draw the diagram myself, because I just think it's a lot easier to understand. So the ideal vapor compression cycle is going to look something like this. Compressor, point 1, point 2 is condenser, point 3 is an expansion valve, and point 4 is the evaporator. And you're going to follow this pattern like this. Okay, and obviously it operates in a cycle. So this is your TS diagram, and you're going to have saturation line like this. Point 1 to 2, the compressor. This is isentropic because entropy is constant. This is then going to pass down here along and then down like this. And you've got point 4 there. You've also got an isentropic point 4S there. Of course, this is point 3. QH passing up like that. And QL, the heat from the low temperature source, is also passing in. You're obviously going to see this 0.12 MPa here at the low pressure before compression, and you're going to see a 0.7 MPa here after passing through the compressor. If you look on slide 9, you'll find a much neater diagram of what I've drawn. You can also find more information on the ideal vapor compression refrigeration cycle on page 610 of the recommended textbook. 0.7 here and 0.2 MPa here. Mass flow rate 0.05 kg a second. And part A of the question, we're interested in the rate of heat removal, which is QL from the refrigerated space. So that's this value here that we're interested in finding, and simply that can be written by the mass flow rate by the change in apathy from point 1 to point 4. So H1 minus H4, simple equation for that. For part B, we're interested in the power input to the compressor. So we're interested in QH, and of course we're interested in the change of apathy between points 2 and 3. So QH is equal to the mass flow rate H2 minus H1. As a result, we're interested in the values H1, H2, and H4. Mass flow rates given. Okay, and also it's worth noting, since the process 3 to 4 is a throttling process, it's isenthalpic, so there's no change in enthalpy. So H3 is equal to H4. Because the ideal vapor compression cycle on entry to the compressor R38 is saturated vapor at the lower pressure value, we can use table A12 on page 21 to calculate the value of H1. And we can do this. H1 is equal to Hg, saturated vapor, at a pressure of 0.12 megapascals. This can be found using table A12 on page 21 of the Thermodynamics property table booklet. And You can also, and it gives a value of H1 equal to 236.97 kilojoules per kg. Similarly, for entropy, S1 is equal to Sg at pressure 0.12 MPa, and we get a value of S1 equal to 0.94779 kilojoules per kg. We found H1, this value. Bearing in mind process 1 to 2 is an isentropic process. If you notice the straight line here, this here, S1 is equal to S2, and hence there's no change in entropy from points 1 to 2. 2 is isentropic, therefore S1 is equal to S2. Therefore, since S2 is greater than Sg at 0.7 megapascals, which is shown here, 0.94779 is greater than 0.91994. Therefore, refrigerant 134A is superheated. So, with this in mind, we need to use table A13, and we're going to have to interpolate to find the corresponding empathy value for the S2 value that we've got. Okay, I'm briefly going to run through the interpolation to find the corresponding H2 value enthalpy for the S2 that we found that was equal to S1. You already know how to interpolate. Of course, you can skip this part of the video. Okay, the method I'm going to be using uses the equation. The value we're interested in lies at this particular point here. These are our values. Okay, so that's our particular value, and the H2 that we're looking for is here. Okay, so the equation for interpolation y2 is equal. You don't have to use the equation's not given, so if you want to use it, you need to learn it. There is another method that you can use as well. Of course, you might have seen it in the model answers that Dr. Ranting has put together. It's up to you which method you use, whichever you find quickest. Try them both. Okay, y1, y2, y3. Of course, y2 is H2, and this is what we're trying to find. Y1 is quite simply 645. Which gives you a value of y2 equal to H2, which is equal to 273.54 kilojoules per kg. Now we have H1 and H2. We're able to calculate the compressor work. We know Win is equal to mass flow rate H2 minus H1, which equals 1.83 kilojoules per second, which is also kilowatts, of course. Now, in order to find the rate of heat removal, we need to find H4 or H3, because remember, we know that H4 is equal to H3. Enthalpy at this process is constant at point 3. Pressure is equal to 0.7 MPa, and the refrigerant R134A is saturated fluid. Therefore, from the table, H3 is equal to H at 0.7 MPa, and H3 is equal to 88.82 kilojoules per kg. So finding QL is now just a simple calculation. QL is equal to M dot H1 minus H4, which is equal to 7.41 kilowatts. Okay, now we're interested in finding the rate of heat rejected to the environment. In order to do this, we should consider that QL and Qin represent the heat removed from the cold space and the work from the compressor. This energy has to go somewhere. So therefore, QH, heat rejected to the environment, is equal to QL plus work into the compressor. Simply what we've previously calculated, 7.41 plus 1.83, which is equal to 9.24 kilowatts. Note that QH can also be calculated directly using the same method of QL and Win, but since we already found those two values, it was easier just to add them. But of course, had you have not done that, you could have quite easily used the below equation, and you'll see that you get the same answer. Okay, finally, to find the coefficient of performance of the refrigerator, for part C, the equation is given on the data sheet, and you know that it's cooling effect divided by work input. So it's QL divided by Win, and they'll give you 7.41, 1.83. So the COP of this particular refrigerant, coefficient of performance, is 4.05.